Okay, why don't we go ahead and get started. I think to begin with, I'd like to remind everybody to complete the survey. Did you say that you have extra copies back there, or is that where they're supposed to?
Copies of the survey back here. If anyone didn't get one, then you can leave it in the pile back here when you're done.
You can leave it in the pile there, or give it to one of us, and we can take it for you. Okay, now I put the. Are you guys ready for the final exam now? Let's try it. Remember what I said? We can have open book and open notes and everything like that. And also, it's a group exam, so let's try it. So how about 1A right here? Give an example of a badly approximable number. It has to be a closed form using plus, minus, times, divided, and nth root. Raise your hand if you want to try to answer this one. Say it again? Oh, okay. No, I want to know if anyone can give me an example of one. I can help you as well. Okay, the square root of 3 is 1. How do you know?
Because I attended your lecture earlier.
Oh, okay. All right. That is an example of one. I would say the simplest example that you could give would be the golden ratio. And how would you know that? How would you prove that that's badly approximable? Well, badly approximable is equivalent to having bounded partial quotients. Take the simplest possible continued fraction expansion you can think of, which is all ones, and you should know by now that that continued fraction is the golden ratio, 1 plus the square root of 5 over 2. Okay. Now, part B, what can you say about the size of the collection of badly approximable numbers? It's Lebesgue measure 0. Say it again. Hausdorff dimension 1. So in particular, it's uncountable. Okay, so you guys got so problem 1 is done. All right. Let's try problem 2 now. Problem 2 is a weird problem. It says, prove that for every real number alpha and for every natural number capital N, you can find a fraction little a over n for which this inequality is satisfied. Does this inequality look very strange? It is somewhat contrived. That's the reason why I put the hint right here. The hint is that this inequality, if you rearrange it, this inequality being satisfied is equivalent to the inequality that I've written here being satisfied. N squared over capital N squared plus big N squared times n alpha minus a squared less than or equal to 4 over pi. So do you guys have any ideas about how to do this one? You don't have to have the full solution, but if you have a good idea. You're pretty close. It's kind of like a version of Dirichlet's theorem, but I've changed Dirichlet's theorem a little bit, right? And how have I changed it? Instead of asking for the difference from alpha to a over n to be less than or equal to 1 over little n times big N, which is a pretty simple thing to have on the right-hand side. Now I've sort of changed it up. Now here's the second hint for this problem. If you look at this inequality, if you think about little n as being x, and if you think about this quantity as being y, then this inequality is the same as x squared over n squared plus n squared times y squared less than or equal to 4 over pi. Okay? So what is the collection of all xy's that satisfy that look like? It's an ellipse in R2. The volume of the ellipse is 4. So what do you think? Yeah. The idea is to go back to the proof of Dirichlet's theorem that I gave you using the connection with SL2R. Remember when we looked at the proof of Dirichlet's theorem, we connected it to the Minkowski convex body theorem. We said Dirichlet's theorem is equivalent to the statement that there's a non-zero lattice point in my lattice. The lattice was SL2z times 1 alpha 0 1, some collection of points in R2. The lattice was the lattice generated by the rows of this matrix. That's what I should be saying. And we saw in the first lecture that Dirichlet's theorem is equivalent to the statement that there's a non-zero lattice point in this long, skinny box. The length this way was 2n, and the height was 2 over n. So the volume was 4. It's symmetric about the origin and convex, and so we use the Minkowski convex body theorem. Well, exactly the same proof works now because the ellipse that is defined by this inequality is also a convex symmetric body centered at the origin, and the volume is 4. So we know by the Minkowski convex body theorem that there's a non-zero lattice point in there. Okay? So you see how that one works. Okay, that one was kind of tricky, and I admit that it was a little bit contrived, but I just wanted to remind you about the proof of Dirichlet's theorem using Minkowski convex body theorem. How about the next one, number 3? Does anybody have any ideas about this one? What is this? What is this? This is the two-adic. Well, it's the two-adic absolute value event. So you take the highest power of 2 that divides n, and you take the reciprocal. Why is this true? Let you guys think about that. Oh, OK. While you're thinking, arrange this. There you go. OK, I'm going to give you a hint on, yeah?
Well, so if you look at the term in there, you have n, and then you have the norm and the p-adic norm for n and for 2 and 3. So you can think about that as that's growing and what's happening to it, and you'll find that, well, for every even and say odd integer, this is growing and growing rapidly, so you can have 1 over 2 to the 2 to some power, and so those terms are just going to keep going, so that's growing as 2 to some power, while as n is growing as polynomial, so you have polynomial over exponential growth, so you can imagine that this is going to go down to 0 as n keeps increasing.
Just from looking at these pieces, you mean?
So you have polynomial divided by exponential terms.
Well, so here's the thing. If you think about it this way, whatever n is, it has some prime factorization. It's 2 to the k times 3 to the l times something else. I'll call it n prime, where n prime is coprime to 2 and 3. And when I take n and I multiply it by its 2 absolute value, and I multiply that by the 3 absolute value, what happens is I get n times 1 over 2 to the k times 1 over 3 to the l. So I just get n prime. So the smallest that piece could be on its own is 1. But the idea for this one, the reason why I put this one here is because I actually want to use the idea behind this to connect it to something I'm going to talk about today. The idea behind this one is just don't worry about looking at the collection of all natural numbers n. Just look at the collection of all natural numbers n, which are a power of 2 times a power of 3. So just look at the multiplicative semigroup generated by 2 and 3. Okay? And so what do you get when you do that? Well, the infimum over all integers n of 2-adic absolute value n times 3-adic absolute value of n times distance to the nearest integer of n alpha, that's certainly less than or equal to the infimum over all k l bigger than or equal to 0 of 2 to the k times 3 to the l times the 2-adic absolute value of 2 to the k times 3 to the l times the 3-adic absolute value of 2 to the k times 3 to the l times the distance to the nearest integer of 2 to the k times 3 to the l alpha. OK? Now do you see what's going to happen? These pieces here multiply together to give 1. And so what you have on the right-hand side here is you have the infimum over all k and l bigger than or equal to 0 of 2 to the k times 3 to the l alpha, distance to the nearest integer. And what can you say about that quantity? Say it again.
Should be going to 0 because if you look at that thing, it's not going to be bounded below by any real number greater than 0, so it's less than some epsilon.
How do you know that?
Well, it's not a bounded approximable number.
So how do you know that the infimum of this quantity is 0? If alpha is rational, then it's definitely 0. OK? Actually, I should start over and be careful. If alpha is rational, this is maybe not definitely 0. But the original infimum is definitely 0 in that case. OK? So let's come back to this piece. If alpha is irrational, then what do I know about the collection of all points of the form 2 to the k times 3 to the l alpha? I know that it's dense in the unit interval by Furstenberg's orbit closure theorem, which is a non-trivial theorem. It's not obvious. So because 0 is an accumulation point of this set, in the case when alpha is irrational, I know that this is 0 by the Furstenberg orbit closure theorem. Okay? When alpha is irrational. Okay? When alpha is rational, the result is trivial because you just take multiples of the denominator and you get 0. OK, let's go to the last question now. Can you give an example? This is linked to Valerie's maybe you have another way to do it, but this is linked in some way to what Valerie is talking about. Can you give an example of a non-atomic times 2 invariant measure with entropy 0? You may not know the answer to this, and I'm not going to be able to give you a rigorous proof without completely throwing off the rest of my lecture. Does anybody have any idea how to do this? Well, what you can do is you can think about the orbit of, here's the idea. Here's one way that you can try to solve number 4. And I'm not going to give you all the details. I'm just going to give you something to think about, and I'll let you fill in the details on your own. The idea is that you can start with some subshift on the alphabet 0, 1. Okay? And you can consider your subshift, just like we did in the example a couple lectures ago. You can consider every element of your subshift. You know, your subshift consists of one-sided infinite words in the letters 0 and 1, and it's shift invariant, and it's closed under the shift. You can consider every element in your subshift as the binary expansion of a word in the unit interval. Now, that's great and everything, but how do you connect that idea up with the idea of entropy? Well, the basic idea is this. Let's start. So I should ask somebody to tell me the answer, because I know that there is somebody here who knows it, but we don't put people on the spot. But that's okay. So let's start with the Sturmian sequence. Okay, like for example the Fibonacci word. Start with the Sturmian sequence, or start with the Sturmian subshift. Even better. Okay. No, let me say start with the Sturmian sequence. Okay. W. So W is some one-sided infinite word on the alphabet 0, 1 to the n. On the alphabet 0, 1. It's an element of 0, 1 to the n. And now, I'm going to just tell you the answer, and then we're going to move on, because I need to do the rest of my lecture here. The idea is this. You start with a Dirac mass at the point W, and you average along the orbit. So for each integer n, we let mu sub n equal the sum I equals 0 to n minus 1 of, and now here let me see what I need to do. I think I want to put the push forward under times 2 of the Dirac mass at the point W. So in other words, I go along the orbit of my point, and I multiply it by 2. Maybe I'm actually pulling it back by 2. I can't remember which way I want to do it. Maybe I want to do it this way. Okay, it's one way or the other. This is one of these things where I feel a little bit dyslexic. I think this is correct. You shift your word once, and then you distribute the mass equally among the 2 points in your orbit, and then you shift it again, and you distribute it equally among the points, and you keep going. And we know, because the space of measures is weak star compact, that we can find a weak star limit of this sequence of measures. And it's easy to prove that measure, the resulting measure, will be a times 2 invariant measure. That's how you construct times 2 invariant measures in the first place on spaces like this. Okay? And so this sequence, it converges in weak star topology to some measure mu on the circle, which is times 2 invariant. T2 invariant. And now the only thing that you have left to do, and yeah. Oh yes, I do want to normalize. Thank you. I want to put 1 over n. Okay, thank you for saying that. Yeah. The only thing that you have left to do now is to explain why that measure has entropy 0. But that has something to do with knowing about the word complexity of your word. And because the word complexity is so small, in fact, I didn't even need to pick a Sturmian word to make this work, but I just went ahead and went for the extreme case. Because the word complexity is so strong, you can use this to derive the fact that the entropy of your measure is going to be 0. Okay? Do you see sort of the sketch of the idea there? Okay, so that is the end of the torture part. And now I want to talk about, but I wanted to kind of go back through and resurrect some of the ideas just to give you a chance to think about them one more time and see how things are sort of fitting together. So what I want to do now for the rest of the lecture is I want to talk about another application of the ideas that I introduced last time about invariant measures and entropy. before I begin, I just want to make a couple remarks about the proof that I gave at the end of last lecture, the proof of the weak Rudolph theorem. Number one, I don't think I said this, but the proof that I gave is essentially contained in this blog by Carlos Matthias. I don't know how you pronounce his last name. And he attributes it to Arthur Avila, and that may be true. It may be also attributed to Arthur Avila, but I think the idea, in essence, does go back to Lyons, like we said. Number two, I wanted to patch up one part of the proof, which I think I didn't explain carefully enough. And so this is going to require you to remember, or go back in your notes to remember what we did. So the idea was this: we had a measure mu, which is T3 in T, which is a sigma 2,3 invariant under the action of the semigroup generated by 2,3, and which is T3 ergodic. And with the entropy of the measure with respect to the T2 map bigger than 0. Okay? And the proof that, and the goal was to try to show that that measure is actually a Lebesgue measure. So the way that we did that was we did it in 3 steps. There's nothing wrong with the first step. In the first step, we introduced a new map, which we called psi, I think. And psi was the map which takes x to x plus a half, mod 1. And what we proved in the first step is that the push forward of the measure mu by psi is T3 invariant and ergodic. Okay? There's nothing wrong with that step of the proof. It just follows from both of these steps, they need to be checked, that it's T3 invariant and ergodic. But they both follow in slightly different ways from the fact that the T3 map and the psi map commute with each other. Okay? Number two, I explained this a little bit hastily. So in number two, so this measure we called nu, by the way. The push forward measure, we called it nu. In number two, I tried to claim that mu and nu are not mutually singular. And therefore, they're equal to each other. Because it's 2 different ergodic measures. If they're not mutually singular, then they have to be equal to each other. So this is a true statement. The argument that I gave is a little bit flimsy, because it sort of gives you the idea that if 2 measures have the same support, then they have to be. If 2 measures have the same support, then they can't be mutually singular. But that's not a true statement, in fact. And so I want to go back there and just patch this up a little bit. The reason why I'm doing this is also partly so that I can remember later. If I forget the argument, I can look back at the video and remember how it works. Because one of the students, I think Brian Chung and I, we figured this out in the problem session yesterday. So it's a very easy argument. The idea is this. Let's suppose that they were mutually singular. Let's suppose that the measure mu and the measure nu were mutually singular. Then what that means, let me just write down the definition. It means that we could find a Borel set A with the property that the measure of A complement is equal to 0, and the mu measure of A complement is 0, and the nu measure of A is 0. Okay, so that the measures are supported on complementary parts of the circle. Okay, well, then of course, now if I just use what nu is, what is nu of A? Nu of A is mu of A minus a half. That's just from the definition of nu as the push forward of psi. And so what all this implies is that the measure of A complement union with A minus a half is equal to 0. Okay? So that the union of 2 sets of measures 0 is 0. No big mystery. Well, the fact that that's a set of measures 0, together with the fact that the times 2 map acts with positive mu entropy, means that the complement of this measure 0 set has to contain a pair of points whose difference is 1/2. Okay? So there's no, remember, having positive entropy with respect to the times 2 map means there's no way to throw out a set of measure 0 and make the resulting map invertible. And so the conclusion of that observation is that Therefore, there exists a point z in the circle such that z and z plus a half are both in the complement of that measure 0 set. So that's a complement union a minus a half, all that complemented. OK, well, the complement of that set is just a intersected with a minus a half complement. A minus a half complement is a complement minus a half. And now, can you have a point which is in both of those sets? Well, no, you can't, because if z plus a half is in the set, a complement minus a half, then it means that z is in a complement. And that means that z is not in a. OK? And so that's the contradiction. And that's the way that you rigorously fix that little part of the proof that I stated yesterday. So I wanted to show you that because I want the proof to be complete. The way I stated it yesterday, I think there was a little gap. OK, now I want to talk again about something that I mentioned in the first lecture, and that is the p-adic Littlewood conjecture. I'm actually going to beef it up a little bit. So I think we're at Roman numeral 5 for those of you who are counting. And for those of you who are not counting, we're just at the next section. And the next section I am going to call Applications of Toral Dynamics. It's a slight lie, but it's slightly true as well, to the mixed Littlewood conjecture. Okay. I told you about the p-adic Littlewood conjecture already. I'm going to tell you the full mixed Littlewood conjecture now. It's not that much more complicated. I just need to introduce the notion of a pseudo-absolute value sequence. So a pseudo-absolute value sequence, it's not complicated. D. Let me give the elements of this thing a name. I'll call them ni. I going from 0 to infinity. Is the sequence satisfying n naught equals 1? And each subsequent n divides the next one. Ni divides ni plus 1 for all I. OK? So an example would be you just take all the powers of 2, 1, 2, 4, 8, whatever. More complicated one. Well, there's no really complicated one. This is the definition. It's not a complicated definition. Now, the dyadic pseudo-absolute value pseudo-absolute value, allow me to just abbreviate a little bit. It's denoted by absolute value with a subscript of script d. It's defined by, and by the way, so this is a function which takes, I'm going to define it as a function which takes in integers and spits out non-negative reals. Okay? Is defined to be, well, the dyadic absolute value of an integer n is going to be the infimum of the set of 1 over ni, where ni's are taken from the set of elements of your pseudo-absolute value sequence which divide n. Okay? It's not a complicated thing. You just pick the biggest element of your pseudo-absolute value sequence which divides the integer, and you take the reciprocal. Okay? So simple example, just to orient you a little bit. If my pseudo-absolute value sequence is the one that I mentioned a few minutes ago, if it's a to the power I, where I goes from 0 to infinity, all powers of one integer, then the dyadic absolute value is exactly equal to the adic absolute value that I defined in my first lecture. Just take the highest power of a that divides your integer and take the reciprocal. By the way, the dyadic absolute value of 0 is 0 by the definition. Everything divides 0. Yes? So now I can tell you the mixed Littlewood conjecture. So the mixed Littlewood conjecture, it's also called the Diophantine and Toulier conjecture. It's proposed much later than the Littlewood conjecture, 80 years later. But there's a lot of work, a lot of interesting work surrounding the conjecture, and by a lot of notable people as well. So I think it's a good conjecture. It's proposed as a conjecture that's potentially easier than the Littlewood conjecture, but I actually think it's still pretty hard, it seems like. At least nobody solved it yet. So it's proposed by Diophantine and Toulier. That's sent to Gu, I think. You're right, yeah? Sorry. I think it is. And what it says is for every pseudo-absolute value sequence, D, and for every alpha in R, the infimum over natural numbers n of n times the dyadic absolute value of n times the distance to the nearest integer of n alpha is equal to 0. OK? Now, let me try to get to the point. I can't tell you everything that's known about this conjecture. It would take too long. So let me try to get to the point that, to get to a point from which I can tell you how this is connected to the kind of stuff that we've been talking about. So let me first of all tell you one thing, which is you might remember, so the Littlewood conjecture, this famous conjecture in Diophantine approximation, it says that for any alpha and beta in R, the infimum over natural numbers n of n times the distance to the nearest integer of n alpha times the distance to the nearest integer of n beta is equal to 0. That's the conjecture. All the mixed Littlewood conjecture is doing is it's taking away this double bar n beta piece and it's replacing it by something which is simulating the values of distance to the nearest integer of n beta. And that thing is exactly the dyadic absolute value of n. Now, one thing that I wanted to say is that I'm just going to write note here, but I'm not going to use complete sentences. I'm going to tell you in words. The Littlewood conjecture doesn't really get any easier if you put in a third real number. Okay? You can, in some cases, you can prove something a little stronger, but there's no new idea. There's no real new ideas that go into the proof. So it's also an open problem to prove that for any alpha, beta, and gamma, the n times double bar n alpha, double bar n beta, double bar n gamma is equal to 0. It's not any easier if you put in a third piece here. Open question. It's an open question to determine for every alpha and beta and gamma, is that true? You might think that it would be easier because you have an extra piece helping to pull the product down to 0, but nobody knows how to prove that either. Now, in the case of the two-adic Littlewood conjecture, remember I told you the p-adic Littlewood conjecture before? It's a special case of the mixed Littlewood conjecture. So the p-adic Littlewood conjecture says that for every integer, for every a bigger than or equal to 2, and for every real number alpha, the infimum over natural numbers n of n times the adic absolute value of n times double bar n alpha is equal to 0. Now, in this case, in the p-adic Littlewood conjecture, here, this was one of the reasons why I put that exercise on the final exam. It actually does turn out to be doable if you add in another p-adic absolute value. So it is actually true that if you have two integers, let's say a and b bigger than or equal to 2, then for any alpha in R, the infimum of n times the adic absolute value of n times the b-adic absolute value of n times the distance to the nearest integer of n alpha is equal to 0. So that follows from the Furstenberg orbit closure theorem. You do actually need to separate out into the cases where a and b generate a Lacanieri semigroup and when they don't. If it turns out that a and b generate a Lacanieri semigroup, it's still actually true. You just need to separate it into two cases to prove that. Okay? So this is true, but it's true for non-trivial reasons. It's true because of the Furstenberg orbit closure theorem. Now, here's the question. In this problem, is it possible to replace, kind of going in the direction of the full mixed Littlewood conjecture, is it possible to replace the b-adic absolute value there by a dyadic pseudo-absolute value, pseudo-absolute value? That's the question. Seems innocuous. Turns out to be somewhat non-trivial. And so the theorem that I want to tell you about to sort of wrap things up here, as we're getting towards the end, is a theorem that I proved with Stephen Harrop We proved it in about 2010, I think. I think it was published a little bit later than that, 2013 or something. And so what our theorem says is, suppose that A is bigger than or equal to 2, and that the elements of your pseudo-absolute value sequence D are divisible by, do I want to give the pseudo-absolute value sequence a name? Just give me 1 minute. Yes, I do, just as in my definition. Are divisible by finitely many primes which are coprime to A. It's a technical restriction that we need here. By finitely many primes. Finitely many primes which are coprime to A. I need to put a comma there to disambiguate the sentence, although it would be silly to say it otherwise. OK. Now, if there exists a number r bigger than 0 such that the logarithms of the elements of the pseudo-absolute value sequence are bounded above by, is that really right? OK. By r. No, that's not right. OK, give me just a moment to think about this here. Give me a second here. Yeah, that's right. That's right. OK. For all I bigger than or equal to 2. Then, for every real number alpha, the infimum over natural numbers n of n times the adic absolute value of n times the dyadic absolute value of n times the distance to the nearest integer of n alpha is equal to 0. OK? So this seems like a really this seems like a very modest result. It seems like a very modest step from the easy theorem that I stated down here, which follows from Furstenberg's orbit closure theorem, to this theorem here, where we've just replaced the b-adic absolute value by a d-adic absolute value. However, you can't prove this theorem by using the same arguments, because in this theorem on the left-hand side here, when we sketched the proof of the exercise at the beginning of class, we looked at the semigroup generated by A and B. We had everything of the form a to the k times b to the l. If we try to follow the same argument here, we're going to have everything of the form a to the k times ni, where ni is just in some pseudo-absolute value sequence. And that's not going to be in general, it's not going to be a sub-semigroup of the natural numbers. If you try to mimic the argument in Furstenberg's theorem, it just doesn't work at all. It completely fails. And so you need some new idea to do this. Now, in the 20 minutes that are remaining, I'd like to try to explain some of the elements of the proof of this theorem. One more definition which I need to introduce here is the definition of upper box dimension, or upper Minkowski box dimension. This is an important definition anyway that everybody should learn at some point. So here's a definition. This is the definition of Minkowski dimension. The definition is, well, let's pick a subset of some compact metric space X, OK? And for epsilon bigger than 0, we will say that a subset B of A is epsilon separated if any two distinct elements of B are separated by at least epsilon. OK, that was a pretty intuitive definition. The distance between alpha and beta is bigger than or equal to epsilon. OK. Now I'm going to make this a little less. Little less of A epsilon denote the largest cardinality of an epsilon separated subset of A. Epsilon separated subset of A. Okay? And then the definition of the upper Minkowski box dimension, or the upper box dimension, I'll just write it that way. The upper box dimension, okay, is the lim sup as let me write the notation. It's dim of A with a bar on top. That's the upper box dimension. Its lim sup as epsilon tends to 0 of the logarithm of S of A epsilon divided by the log of 1 over epsilon. Okay. Now, if you try to compute the Minkowski box dimension of the unit interval, let's say, you're going to find out that it's 1. If you try to do the unit box in the plane, you're going to find out that it's 2. If you do a d-dimensional manifold, you're going to find out that it's d. But this allows you to sort of interpolate between the integer dimensions. So the dimension of the Cantor set is going to be log 2 over log 3. I don't have time to go through all of the details. If you've never seen this before, though, it's worth thinking about and trying to read up a little bit on how it works, and also on how it's connected to something else called Hausdorff dimension. Okay? But for now, let me just ask you this question. Does this definition remind you of another definition that you've seen? What? Yeah, it should remind you of the definition of topological entropy. And for good reason, okay, as you're about to see. The two things are sort of intimately connected together. So let me tell you the sketch of the proof. The proof has 2 stepping stones, and each stepping stone has a giant iceberg underneath it that holds it up. So the first stepping stone is another theorem, and it's in our same paper. And what it says is, well, it says with A and D as in the theorem that I just now stated. As in the theorem, if you have a real number which is not rational, and if we set A of alpha to be the closure of the collection of points a to the L times nk alpha, where L and k are bigger than or equal to 0. So this is kind of like what we did in the Furstenberg orbit closure theorem, except for now maybe this is not a semigroup. We're just taking a bunch of integers on the circle and we're closing it. What can we say about that set? Well, then we can say that the upper box dimension of the set is bigger than 0. Okay? So stepping stone number 1 in the proof of the theorem in the middle of the board is this result, that if you have a pseudo-absolute value sequence which is not too sparse, in fact, even if just the gaps are bounded between consecutive, I mean the ratios are bounded between consecutive terms. That's yeah.
Sorry, can I ask what you mean by an epsilon separated set? You gave an epsilon separated set here.
Yeah, so I defined it here, right here.
Oh, sorry.
It means that it's the same as 0 epsilon separated in terms of the definition from yesterday. Or maybe it was 1 epsilon separated in terms of the definition from yesterday. It means that any 2 points are at least epsilon apart. So OK, so stepping stone number 1 is that, you know, if we had a full non-Lyapunov semigroup here, we would be able to prove that the orbit is actually everything. If we just have something weaker, like in the statement of our theorem here, we can't necessarily prove that the orbit closure is everything. But what we can prove is that the orbit closure has positive upper Minkowski dimension. Okay. And by the way, why I say that OK, let me just tell you theorem number 2. So the second theorem is a theorem of Einzieler, Fishman, and Shapira. It's in that paper that was in the reading notes for the course, one of the project papers. Some of you took a look at this paper. It's a good paper. It does require you to have a lot of background to read it. And I think this is about also 2010. It's about the same time as our paper came out. So one of the theorems in their paper, there's a lot of theorems in there. One of the theorems in there says if mu is a times a is a TA. TA means multiplication by a mod 1. Invariant and ergodic measure. Invariant and ergodic measure with positive entropy. Positive entropy, then mu almost every point is well approximable. So is in the complement of bad. Okay, the complement of bad is the collection of well approximable points. Okay, so let me try to tell you how the proof of the main theorem goes once you know these two things. Okay, I will tell you that. I will tell you that. But first of all, before I forget, I mentioned that these two theorems are both sitting on other big results. The first theorem, the proof of the first theorem rests on a theorem in number theory by Baker and Wisholz, which gives lower bounds for linear forms and logarithms. It's considered a pretty deep theorem, a pretty deep collection of results in number theory, and it's one of the things that Baker got the Fields Medal for. The second theorem rests on a measure rigidity result, which is due to Lindenstrauss, which has to do with measure rigidity in spaces like SL2 of QP cross SL2 of Q other primes, cross SL2 of R modulo lattices. Okay? So the second theorem rests on a measure rigidity result for a diagonal action on some S arithmetic space, kind of like the result for SL3R mod SL3Z, but in a different space. And so now, if you assume that these two results are, if you take these two, I won't be able to explain the proofs of either of these results. It would take a little bit too long. Neither one of them is easy to prove. But what I will try to do is I will try to explain how, if you know those results, how you can use that to finish the proof of the theorem. And the idea is I'm going to formulate this as a lemma. The lemma is this. If I have a subset of the circle, which is a closed set, is closed. If the times A map maps it into itself, so if TA of A is a subset of A, then, just give me a minute to say what I want to say here. And if the upper Minkowski dimension of A is bigger than 0, then there exists a measure, mu, in the space of ergodic measures for the map TA restricted to A with positive entropy. Okay? So what this is saying is if you have a set A with positive upper Minkowski dimension, and if it makes sense to talk about the times A map restricted to A, so that once you start from a point you stay inside the set A, then you can find a measure, an ergodic measure, which is supported on the set A, so that I don't mean that A is the full support, but the support of your measure is a subset of A, and with the property that your measure has positive entropy with respect to the times A map. Okay? So this is, you can sort of see how these things are linking together here. Now, once you know, so give me just a second here. I have about 15 minutes remaining. And I'd like to show you how to prove this lemma, because that's the sort of meat of everything. But I'm going to have to erase some stuff to do it. So before I erase it, let me show you now how to take everything that's on the board and prove the theorem in the middle. Okay? And then I'm going to erase a bunch of stuff, and I'm going to show you how to prove the lemma. So proof of I'll call this theorem 1. Proof of theorem 1, assuming everything that's on the board. Well, it works a lot. OK, so let's suppose that I had a real number alpha such that the infimum over natural numbers n of n times the adic absolute value of n times the dyadic absolute value of n times double bar n alpha were bigger than or equal to epsilon for some epsilon bigger than 0. So let's suppose that I had a counterexample to the statement in the middle of the board. Then what I could do, I'll just show you a sequence of inequalities. All of them are fairly easy to verify. So first of all, I'll rewrite what I already wrote, but in the opposite order. So here I have n, adic absolute value of n, dyadic absolute value of n, distance to the nearest integer of n alpha. OK, well, that I can write that that's equal to the infimum over all natural numbers m and all k and l bigger than or equal to 0 of m times a to the l n k times the adic absolute value of m a to the l n k times the dyadic absolute value of m a to the l n k times the distance to the nearest integer of m a to the l n k alpha. I haven't really done anything here. I've just written the integers all in a different sort of form. Now what I want you to observe, though, is that the adic absolute value is an absolute value. And it always takes values less than or equal to 1. So the quantity here, the adic absolute value of m a to the l n k, is less than or equal to 1 over a to the l. It's at least that small. The dyadic absolute value of this number is less than or equal to 1 over nk. It might be smaller if m happens to have an extra, if when you throw in the m piece, what you get is divisible by nk plus 1, this might be smaller. But it's at least as small as 1 over nk. So when I combine that information together, I get that this infimum is bounded above by the infimum over k and l bigger than or equal to 0 of the infimum over natural numbers m of, now let me just be a little bit careful here, m times distance to the nearest integer of m a to the l nk alpha. OK? Say it again. nk is the kth element of my pseudo-absolute value sequence. Now, if you think about it, just read the left-hand side of the inequality as epsilon is less than or equal to the right-hand side of the inequality. What does this mean? This means that all of the points a to the l times nk alpha, they're all, with l and k bigger than or equal to 0, they're all in bad epsilon. That's the definition of what it means to be in bad epsilon. And in fact, since this is bad epsilon is a closed set, so it means that the closure of the set is in bad epsilon. But this set is an A invariant set. So you can use this set to, I'll just say it this way. You can use this set together with the theorem on the far left-hand side. The theorem on the far left-hand side tells you that the dimension of that set is bigger than 0. Yes, and so you can use this set to construct A times A invariant and ergodic measure with positive entropy supported on a subset of bad epsilon. Okay? But that's a contradiction, because the Einsiedler, Fishman, and Shapiro theorem tells you that if you have such a measure, almost every point with respect to that measure must be well approximable. So it's a contradiction. So the contradiction implies that there are no counterexamples to the. It implies the statement of the theorem. So this implies contradiction. Okay? Now, you can write that down and think about it. I need to start on the proof of the lemma, or I won't finish it. So how do you prove the lemma? This is a sort of an exercise in definitions, but it also involves using the variational principle and the ergodic decomposition. It's not that long, but it's a cool little proof, and I'd like to show you how it works. How do you extract from knowing that you have a times A invariant set with positive upper box dimension? How do you extract that you can get a times A invariant ergodic measure with positive entropy? OK, let's take a look at that. Proof of lemma. Let me back up a little bit here. OK, first of all, let me just write D for the upper dimension, the upper box dimension of A. And of course, we're in the lemma, we're assuming that D is bigger than 0, right? OK, good. Yes. OK. Now, by the definition of upper box dimension, I can choose a sequence of epsilons. I'll call it epsilon sub m, decreasing to 0, with the property that the limit as m tends to infinity of the logarithm of the largest cardinality of an epsilon m separated subset of A divided by the log of 1 over epsilon m is equal to D. Okay? I'm using the definition of limit. So then, the definition of lim sub. So then, for every delta between 0 and d, I can find an integer m naught such that the largest cardinality of an epsilon separated subset of A is bigger than or equal to 1 over epsilon m to the power d minus delta for all m bigger than or equal to m naught. This is the definition of limit. Okay? Just rearranging the formulas and taking the exponential, and this is what you get. Okay? So fix such a delta and such an m naught and m naught. Oh, and m bigger than or equal to m naught, sorry. And choose a number n such that epsilon m lies between a to the minus n and a to the minus n plus 1. Okay, I can always do that, of course. Now, pick an epsilon m separated subset of the set A. Call it alpha 1 to alpha k. Once I write stuff on the board here, I'm going to back up and I'm going to tell you conceptually what's going on here. Is an epsilon m separated subset of A of max cardinality Well, I know the cardinality of an epsilon of a maximum epsilon m separated subset is at least 1 over epsilon m to the d minus delta. If I combine that with my inequality here relating epsilon m to the powers of A, just do the inequality, and what you end up getting is that of maximum cardinality, then the cardinality of the subset is at least a to the power n minus 1 times d minus delta. I know this because I did it before class to make sure that it's correct. And also, just from the definition of what it means to be epsilon m separated, I know that the difference between any two elements of the set is bigger than or equal to a to the minus n for I bigger than or equal to 1, less than j, less than or equal to k. Okay? So let me tell you what I'm doing. I'm starting with the fact that the upper Minkowski dimension is positive. What that means is that when my epsilon is in the range between a to the minus n and a to the minus n plus 1, I've got to have a lot of points. I've got to have a large epsilon separated set. Okay? The number of points on my set has got to be at least, where did I write it? This large, a to the n minus 1 times d minus delta. Okay? Now, this is an a to the minus n separated set. Now I want to translate this into the language of topological entropy, and I want to go ahead and start taking multiples by the times A map. That's going to move points apart, of course. But if I sort of fix some sort of threshold, if I say I want to know something about how big n 1 over 2a separated sets are, well, I'm going to allow n to go to infinity as epsilon tends to 0. Okay. So let me write down the calculation for you now. It follows that this is one of these things that you have to go away and just think about it a little bit. It follows that there exists a number L from 0 to n with the distance in the the distance to the nearest integer of alpha to the L, that should be a to the L, times alpha sub I minus a to the L times alpha sub j, bigger than or equal to 1 over 2a. Okay? And so what that means is that the set that I've chosen, this alpha 1 to alpha k, is n comma 1 over 2a separated with respect to the multiplication by A map with respect to TA. Okay? So remember in the definition of topological entropy, there's a double limit. There's a limit over epsilon and there's a limit over n. And what I'm essentially doing is I'm fixing the epsilon threshold and I'm letting n tend to infinity. So I'm starting off with the definition of Minkowski box dimension, and I'm looking finer and finer to find 1 over a to the n separated sets. But then when I move to the dynamical world, I'm allowing myself to move further out in the orbit. It moves the points apart, but I'm getting more and more points. And now let's do the calculation for topological entropy, and let's see what happens. Okay? So therefore, when you go to do the calculation for topological entropy, well, you get that the lim sup as n tends to infinity of the logarithm of S sub n, the largest cardinality of an n epsilon separated set for the multiplication by A map restricted to the set A, divided by n. Well, when I take the logarithm of this number, and then I divide it by n, and I take the limit as n tends to infinity, what I get is something. Okay, so it's the lim sup as n tends to infinity. So what I get is something which is at least as big as the limit along the subsequence, which is d minus delta times log a. Okay. Delta was arbitrary. So now we take delta to tend to 0. And what we get now is that the topological entropy, we did all the hard work right now. This is all the analysis that makes you cry, that you have to do like a day before lecture. You should never wait like the morning of lecture to do these kind of calculations. But then now we're at the part where we get to, rejoice and like run around in the field and stuff, because the topological entropy of our map is at least as big as, I just take the limit as delta tends to 0. It's at least as big as d times log a. So the upper box dimension of my set A times the logarithm of my multiplication by A. Okay? Bingo. Now what? I know the topological entropy is positive. Okay? And so what am I going to do next? By the way, what am I trying to prove anyway? Maybe it's good to go back and think about that. I'm trying to prove that I have an ergodic measure with positive entropy. It's going to be times A invariant and ergodic with positive entropy. So how do I get from this statement to that statement? I haven't even said anything about a measure yet. Say it again. Bingo. By the variational principle. The variational principle tells me that if I take the supremum over all the measured theoretic entropies over all times A invariant measures, I'm guaranteed to find ones that are arbitrarily close to this. Okay? And so by the variational principle, there exists a times A invariant measure. So I'm going to be careful about my statement here. I'm just claiming that this is a times A invariant measure. Hey, by the way, I don't like writing the bar in the big A. I really mean the times A map restricted to A here. Is that okay? So I think I put X in here before, so I'll just put A in there, and that sort of fixes the problem, doesn't it? So there exists a times A invariant measure on times A on the set capital A with positive entropy, with the entropy of mu with respect to TA bigger than 0. Okay? In fact, I can get it as close to that quantity as I want, so I can make an even a little bit stronger claim if I wanted to, but I don't really need to finish the proof of the lemma. Now, are we done? We're almost done, but we're supposed to be claiming that there's an ergodic measure. So how do we finish the proof? Yeah. So now we use the ergodic decomposition. So by the ergodic decomposition, there exists a probability measure lambda supported on the probability measure lambda on the space of invariant measures with respect to Borel sets on that space. You know what I mean? There exists a probability measure lambda. I'll go ahead and write a few more words to deconfuse people here. On MT of A, supported on a subset of the ergodic measures on E, TA, such that mu, my measure with positive entropy, is equal to the integral over the ergodic measures of m d lambda of m. Okay? And now I'm done, because now, remember I mentioned before that entropy is affine. And what that means, even for integrals, is that if I have, what it means is that the entropy of a convex combination is the convex combination of the entropies. Okay? And so it works even for integrals, and you get that the entropy of mu is equal to the integral over the ergodic measures of the entropies of these of m. Okay? I'll just omit the dependence on this map T. So the entropy of mu is equal to the integral over the ergodic measures of the entropies of m d lambda of m. And so that implies that we're done now, because for those who can't see, the conclusion here, I'll find a place to write it down. So that implies that there exists a measure in the ergodic measures with positive entropy. Okay? In fact, it implies that there's a positive lambda measure set of such measures. Okay? So there's one at least. And that's the end of the proof. Okay, well, my time is up. And so I hope that I've given you at least a flavor of how some of these types of arguments go. And I hope that I've also told you some things that might be useful if you're trying to study some of these papers to try to understand the bigger framework and see how all these ideas fit together. I'll stop there. Thank you very much for listening.